Hello everyone, this is Pooky Codes and welcome back to part 8 of Neural Networks Explained, and we will look at calculus for neural networks as well as cost functions. So let's get started. We've seen lots of neural networks, but each time the weights and the biases were given by me. Now, you may think that it's feasible to find the weights and the biases by hand for small problems like the XOR, but it quickly becomes impossible when, for example, you want to detect whether an 50 by 50 image is a dog or a cat. Because if you do the math already with the layers, if there's only an input and an output layer, there's going to be 50 times 50, so 2,500 weights, at least 2,500 weights to find by hand. And this is impossible. So here comes backpropagation. So the neural network starts by initializing all his weights and biases at random values around 0, and then you start accumulating training data, so lots of images of dogs and lots of images of cat. And what you do is that you feed this cat image to the neural network and you say, hey, I want you to give me a 0. And then you'll feed a dog image and say, hey, I want you to give me a 1. And you'll do that so on and so forth and so on and so forth until the neural network finally learns and say, yeah, now I know how to detect a dog or a cat. But how do they actually do that? It's something that needs calculus. So we're first going to start by introducing the cost function. So basically, when our neural network is fed the dog, it's going to output a output. So it's going to say, I think this is a 0.3. But then it's supposed to be a 1, because let's just make it clear this time. 1 for dog, 0 for cat. 1 for dog, 0 for cat. Alright, now we're clear. So it's I'll give a 0.3, and then I'll be like, hey, I don't want that. I want a 1 because it's a dog. So here comes the cost function, and this allows us to find a numerical way to analyze whether the neural network is performing really great or really bad. So there are numerous cost functions, but they all have one thing in common. If the outputs is pretty much the same as the expected answer, so for example, if they say 1 and it's supposed to be 1, the cost function should be low. And if it's not what they want, like very far away, so like when the neural network gives a 0, but you're expecting a 1, the cost function should be higher. So, in other words, the cost function is going to penalize when you're making large mistakes, when a neural network is making mistakes. So, basically, when you got the cost, it's going to learn how to adjust its weights and biases using gradient descent. But to dive into that, we first need to learn the fundamentals of calculus. So, other examples of cost functions before I jump right in is the mean squared error. And basically, the mean squared error, it takes the predicted minus the expected, and then it squares that and you multiply that by 1/2 for a scaling factor. It's just a coefficient. You'll see that it's useful later on, but for now you just think of it as a scaled down version. And what this means is that basically when predicted minus expected is very large in both the negative and the positive ways, it's going to penalize it harder. And for the mean absolute error, for example, when I have just the absolute value of predicted minus expected, it's just going to be like this. So basically, if predicted minus expected is high, it augments linearly the error. The cost, I mean. So, gradient descent is a technique that allows us to minimize a function at a certain position by saying where to go next. So for example, if I had this would be like if I started here, I would just go down, 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 and down. And this is what gradient descent looks like. So it's going to take steps in the right direction to reduce the cost function. So now we're going to do a full-on course on calculus, and you don't really need to know anything about it. You just need to listen and enjoy the ride. So in calculus, there's a concept called derivatives, and it is used to calculate the slope at a certain x of the function. So basically, if I have this function f of x, which looks like some sort of roller coaster, I know that at the point -3, if I draw a line, if I drew a straight line that passed only by this point, the tangential line, I know that it's going to give me a slope of 0. Because it's pretty flat. So flat equals 0. And for example, at x equals 5, I have this line that only passes through this point. And then I'm going to be like, yeah, that's a slope of 1. And you can do that for every point in a function. So every point in this function has a certain slope. So for example, this is a slope. So something like 0.5 maybe. This is something maybe like 0 again. This could be something higher, like, I don't know, 2 or 1. And then, for example, here it could be something negative. So at this point, it's going to be like -4, for example. I don't know them by heart. It's just, it's just to get the idea. It's not really important, the numbers. So in formal notation, this would mean that f prime of -3 is equal to 0. So the derivative, the slope of the line at the x equal -3 is 0. And also f prime of 5 is equal to 1. So the slope at x equals 5 is of 1. So the prime is used that you put in front of a function at the top. It's to say that you're taking the derivative of this function. So an alternative notation is that, as you may know, slope, when you recall your elementary or whatever classes, you'll know that the slope is just the change in y over the change of x. So this is what this means. So df over dx. But here we're not using the delta sign. We're using d, and that's for a differential. But basically, it's fun to know that df over dx just represents the slope at a point, but the instantaneous slope. So basically what I just meant. So the slope, if you had 1 point, so 1 point at -3, and then you had a slope, a line that only passed through this point. So df over dx of -3 is equal to 0. Similarly, the slope at x equals 5 of the function f, so this gives me df over dx of 5 is of 1. So f prime of x gives the slope of the function f at x, that's by definition, and df over dx of x, which is an equivalent notation, gives the change in f over the change in x at the point x. And we know that the change in f over the change in x is equal to the slope. So the both notations are equivalent. So as a recap, a derivative is simply a function that gives the slope of another function at a certain point. So let's say I have another example. So I have f of x is equal to 3 times x. So what is the derivative at x equals 5? At x equals 5, we see that it's a slope of 3. And now I'm asking, what's the derivative at x equals -3? And as you can see, it's still a slope of 3. So basically, if you had any form of linear equation, such as 3x plus 5, 3x minus 3, 2x plus 5, it's just equal, the slope is just equal to the coefficient in front of the x. So in this case, 3. In the case of 2x plus 5, the slope is going to be of 2. Minus 5x minus 3 is going to be minus 5. So the answer for this question in particular is 3. So the derivative of f of x is equal to 3. In other words, f prime of x is equal to 3, or df over dx equal to 3. And notice how I'm not putting any value, so f prime of 5 or f prime of 0, because I'm saying that for all x, they're all equal to 3. And the same case here. So for all x, it's still equal to 3, the slope. So that was great. So we're now going to proceed on to another concept which is called the chain rule. So the chain rule is a very, very important rule in calculus, and it allows us to calculate the derivatives of composition of functions. So what this means is that it allows me to calculate the slope of a certain function where that function is actually a function applied to a function. So we'll see what this means. So given a composition of function, f of g of x, which means you calculate g of x, and then you do f of that. Then df over dx, so the slope of f over x is equal to df over dg times dg over dx. So the change in f over the change in x is equal to the change in f over the change of g times the change of g over the change of x. And as a mnemonic, I like to think of it like that. It's not entirely true, but you can think of it as like the dg just canceling them out when you multiply them, and you'll see that you're ending up with df over dx, which is the left-hand side. So basically, chop chop. This gives us the answer on the left and the right, which is the same thing. So now we're going to make an example. So according to George F. Simmons, I found it on Wikipedia, which is very nice. If a car travels twice as fast as a bicycle, and a bicycle travels 4 times faster than a pedestrian, then the car travels 2 times 4 equal 8. So 8 times faster than a pedestrian. So now you guys will be like, pretty obvious, pretty intuitive. Of course I know that. How is that related to calculus? So basically, we're going to say that dc over db is the ratio between the speed of a car and a bicycle, and db over dp is the ratio between the speed of a bicycle and a pedestrian. Now we want to calculate dc over dp, which is the ratio between a car and a pedestrian. Thus, dc over dp is actually just equal to dc over db times db over dp. So 8 is equal to 2 times 4. Quick maths. Nice. So I hope you gotta make sure that you understand the chain rule and derivatives correctly, because that's very important for the next video. But now we're going to do another topic, which is called partial derivatives. And this is actually something you'll see in multivariable calculus, but you guys are going to do great. So now let's suppose we have a function that doesn't take only one input. It takes 2 inputs, so an x and a y. So for example, if I have f of x, y is equal to 3x minus 4y, then we can calculate partial differentials. So a partial differential is denoted del f over dx, so pronounced del like your computer, and it just means the change in f when you assume everything is constant and you only change x. So what this means is that this is what f looks like. So f of x is equal to 3x minus 4y, or similarly z is equal to 3x minus 4y. You'll see that it looks like some sort of sheet of paper, and this means that if I slice the plane, where, like for example, if I slice the plane at y equals 0, meaning I keep y constant and I can freely move x, you'll see that when I slice it, it gives me a slope of 3. So this is what you see. You'll see that the intersection, when you keep this constant, when you slice your function with y equals 0, you'll see that it gives us an intersection where the slope is of 3. So as you can see, this is the x-axis and this is the z-axis. And as the x-axis augments, you'll see that it's going to have a slope of 3. So this makes sense. Therefore, we say that del f over del x at y equals 0 is of 3. Now similarly, if I said, for example, if I kept y another constant like y equal to 2, you'll also see that it gives the same slope. So it gives a line. This is the intersection when you slice the function off, and you'll see that it gives us a slope of 3 here. where this is the x-axis and this is the z-axis. So if you do other slices, you can do as many slices as you want, and you'll see that it will always give us a slope of 3. Thus, del f over del x is equal to 3. Now, it's the same thing for del f over del y. So we'll take a slice where all the other variables, in this case x, is constant. So instead of doing y equals 0, y equal to 2, I'm going to set x equal to 0. And then I'm going to put y in this axis, so moving forward. And then I'm going to put z on this axis, so this just looks like a normal Cartesian plan. And you'll see that this gives us a slope of -4 at the intersection. So basically, del f over del y at 0 is equal to -4 at x equal to 0. If you do other values of x, for example, x equal to 5, you'll see that even though GeoGebra kind of hides the plane, it's still the slope of -4. So that's good to know. So del f over del y is equal to -4. So the approach without these fancy GeoGebra visuals would be that I have a function, f of x, y is equal to 3x minus 4y. So what I'm going to do is that I'm going to say del f over del x is just equal to del, so in what is f, is 3x minus 4y over del x. And then we know that minus 4y is a constant, as I told you before, we keep the other variables constant. And 3x, it's just a line with a slope of 3. So basically, this is the equation of a line. A slope times x minus a constant, or plus a constant. So what is the slope of this? It's 3. Similarly, for del f over del y, it's del of 3x minus 4y, and this time it's over del y. And then I have a line with slope of -4, and then I have a constant added, which is 3x. So x is a constant in this case. And we get that this is just equal to a line with a slope of -4. And this is good. And we just did the same thing, but this time without the visuals. In other words, the mathematical approach is that you just calculate the derivative of the variable of like x, if you're doing del f over del x, by assuming that every other variable is a constant. So y is just a constant, so basically you don't need to do anything with it. So as a recap, a derivative is a function that gives the slope at a given point. A partial derivative indicates the slope of a slice, where everything else is constant except for the variable you're looking at. So del f over del x, you're looking at x, so this can move and everything else is constant. And the chain rule is that given f of g of x, then df over dx is equal to df over dg times dg over dx. So that was all. I know this course was a lot harder than every other courses, but if you persevered, you guys are doing great. So let's continue on with the next video. So bye-bye. So thanks for watching. If you like this content, like, subscribe, do all that good stuff. And in the next video, we're going to look at gradient descent and backpropagation. So stay tuned. Thanks for watching. If you like this content, like, subscribe, do all that good stuff. And in the next video, we're going to look at gradient descent. So stay tuned.